I was thinking of taking a rest. I have a terrible headache and a cough and cold. So I will spare my throat a bit, and I anyway have a problem there.
Professor Dev has also joined.
Yes, yes.
Okay, hello.
Yeah.
Hi, everybody.
And I think
Yeah.
a couple of students have probably joined too.
Okay. Bhupendra, would this evening be a good time, some time for me to call you for a completely different issue?
Sure, no problem.
Okay, okay, thanks.
I think Professor Das has joined too.
Okay.
Okay.
कपड़े लंबे रहते तो बचपन से आज से कपड़े नहीं खरीदते
लंबी करके पहन लेते। मैं तो 9th क्लास के कपड़े अब तक आते हैं।
8 बंदों ने ज्वाइन कर रखा है जिसमें से 4 होस्ट को होस्ट है।
पीछे कोई आ रही है ना तुम्हारे राइट में वो सेम कलर है।
Don't see Professor Poti and Professor Agarwal yet.
Ah, right. Oh, Professor Pati had mailed earlier that he may not be able to join for the entire event, but
Okay.
he'd be there for his talk slot.
Okay, same for me. I have to leave by 3:30.
Ah, I see. I see. Okay. So I've started the YouTube live stream now. Maybe should we wait for a few more minutes before more people join? Or
How many students have joined?
currently 2 people had joined, I think, Anupam and Mohit. But I think since this would anyway be on the YouTube channel, TCG Crest YouTube channel, this is something that students can always see even at a later point.
Roughly, how many have applied tentatively?
Sorry?
How many have applied? I mean, how many students that is?
I see. I think Professor Das is on mute.
Yes, he is.
He is, yeah. Okay, he's on mute, but I think he's not able to hear us somehow.
No, that is true.
Yeah. So have you started live streaming?
Oh, yes. I've started live streaming.
And how any students who joined?
No, that was my question also.
Okay.
How many have joined?
Okay. That was okay.
I think there's one student, probably one person on YouTube. Zoom, there were a couple of them.
Okay. Mm-hmm.
Wait for about 5 minutes or so. There's at least some critical number.
Yeah.
Sure. Yes. Yeah, because it's on YouTube, people can anyway still see the video at a later stage, even if they don't. Yeah, yes.
Hello.
Yes, hi Snehal.
Yeah, hi. So it has been started.
I think we thought we could wait for some time before more people
Oh,
join,
okay.
that we could start.
Yeah,
The live streaming is,
okay.
of course, on already on YouTube.
Yeah, okay.
So how many on YouTube now?
Um, I think there are 2 of them on YouTube currently.
Okay. Okay.
But of course, this will be also on our TCG Crest channel after the live
Okay,
stream
okay.
ends.
I see. I see.
So, students can always see it on our channel anytime.
Mm.
Professor Agarwal has joined now.
Mhm.
Yeah, hello, I have joined.
Yeah, right.
People. Hello.
Yes, Oshik.
Yeah, I think I'm audible now. Right.
Okay. Professor Das, should we start now? Or
We can. I mean, we can. I guess. Hopefully, more people will join as time goes on. Yes, I guess. Yeah, if you all agree, we can start. Yes.
Or we should wait just for a few more minutes, because if there are not too many students, probably in discussion will not need such a long time. So if
Right.
you just eat into the next part, it's not a problem, I guess.
Okay.
As having a few more students at the beginning, it'd be better.
Yeah.
How many have assembled? I can see 12 or 13 now. But this includes us also.
Yeah.
Mhm.
Yes, yes.
Well, a
There
few
are
more have
16.
joined now.
Yeah, there are 16 participants at this
16,
point.
okay.
Yeah.
And on YouTube?
I think there are 3 of them on YouTube at this
Okay.
point.
But I think on Zoom, most of participants are from our center, except maybe one
Yes.
or two.
Yeah, maybe there are 4 or 5 students at this point.
The number of students is slowly increasing.
Yeah.
We can just wait 1 more minute and then start, I guess.
The effect of Indian stretchable time. IST.
Yeah, maybe we can start in a minute. Yes, yes. Okay.
Yes, maybe we can start now. So if you can, Prasanna,
I think so. I think so.
Yeah,
Okay.
maybe you can, yeah, please. My slides, if you can show that, Prasanna.
Yes, yes, sure. I'll just share my screen.
Yeah.
So are you able to see these slides?
Yes.
Yes. Okay. So
Okay, I always forget what's for the full screen. Yeah, enter full screen. Okay.
right. Okay.
Okay.
Okay. So let's start. So let me begin by welcoming all of you to today's event, particularly the prospective PhD students. So my name is Bhanu Pratap Das. I'm the director of the Center for Quantum Engineering Research and Education, which is a center within TCG CREST. And CREST stands for Centers for Research and Education in Science and Technology. So our focus is on quantum computing, quantum communication, quantum sensing, and also quantum materials. All of these areas are the current focus of the National Quantum Mission, which will begin very soon. And this is the biggest science project in the history of India. And that's very appropriate because quantum science and technology, in particular quantum computing, quantum communication, quantum sensing, currently the hottest areas in the whole field of quantum science and technology. Our center was established in 2020, and we currently have 9 faculty members, 3 visiting faculty members, 2 visiting scientists. We also have a quantum engineer who works mainly on quantum software. Then we have 4 postdoctoral fellows, 10 doctoral students, because the doctoral program is rather new. It started in 2022. And we have 5 project associates and 2 research interns. Okay, so the next slide. Yes, the objectives of our center is to carry out cutting-edge research in both experiment and theory in the field of quantum sciences and technology. And as I said, that includes quantum computing, quantum communication, quantum sensing, and quantum materials. We have a very eminent scientific advisory board, which consists of leading international scientists in the field of quantum science and technology. That is Professor Arthur Eckert from Oxford University and the Center for Quantum Technologies in Singapore, Professor Yasunobu Nakamura from University of Tokyo and Riken. He's the inventor of the superconducting qubit. That is the basis of superconducting quantum computing. Then we have Professor Kenji Omori, who works on neutral atom quantum computing. He's from the Institute for Molecular Sciences in Okazaki, Japan. And we have Professor Hartmut Hefner from University of California, Berkeley, and he's the director of the Quantum Computing Hub at the University of California, Berkeley. So you have three cartoons for quantum computing, so depicting qubits and the entanglement between qubits. This is just to show that quantum computing is one of the areas of research at our center. Okay, so the next slide. Yeah, so the research we carry out has both a theoretical component as well as an experimental component. I'll begin with the theory first. And in theory, we work on quantum computing, quantum information and communication, as well as quantum machine learning. So this is a combination of quantum physics, quantum chemistry, and computer science. Now, in quantum computing, when we want to solve a particular problem on a quantum computer, we define the problem. And for that problem, we have to find a method of doing it on a quantum computer. And that's called a quantum algorithm. So anytime we solve a problem on a quantum computer, you have to have a quantum algorithm. So we have applied existing quantum algorithms, modified them suitably, and used them for solving problems for atoms and molecules. That is, we've looked at atomic and molecular properties, and we have tried to compute them using existing quantum computers, using algorithms, suitable quantum algorithms. There are two kinds of computers. The first kind is called gate-based because it has qubits and quantum gates. And the second type is called a quantum annealer, which only has qubits. We have solved problems using both types, gate-based quantum computers as well as quantum annealers. And the quantum algorithms that we have used are suitable for existing quantum computers with about, say, 20 to 30 qubits. And there are algorithms for such quantum computers. So, and then we have algorithms that are more suitable for long-term quantum computers. Those are called fault-tolerant quantum algorithms. We've used both near-term quantum algorithms and more long-term quantum algorithms as well for computing atomic and molecular properties. And we have collaborated with research institutes and universities inside India and outside India as well. In India, we have worked with groups from the Physical Research Laboratory and IIT Bombay. And as you can see in the slide, we have collaborated with groups in Riken, University of Tokyo in Japan, Keio University, as well as IBM. And we also are collaborating with University of Wisconsin-Madison, which is one of the leading groups in quantum computing in the world. And we also work on the computer science aspects using complexity theories for different algorithms, and also quantum machine learning. And there we have collaborators from Italy, Australia, and the UK. And the long-term quantum computers need error correction. So because of the noise in a quantum computer, so there are methods being developed for quantum error correction. So we also work on that. And there we collaborate with Center for Quantum Technologies in Singapore. And more recently, we have been working on quantum information and communication. And there we have collaborations with many universities and institutes in India, outside of India. And you will hear more about these topics as we go along. And I've just mentioned the publications in quantum computing because quantum information is rather new at our center. So we have published about 30 papers in the last 2.5 years in leading journals like Physical Review Letters, Scientific Reports, Physical Review Research, Journal of Chemical Physics, European Physics Journal Plus. And this is to do with quantum algorithms being used either on classical computers or quantum computers. Okay, the next slide. So one of the major objectives of our center is to actually build a superconducting quantum computer. So what you see on your left is a dilution refrigerator, which is absolutely essential for building a superconducting quantum computer because you have to do the experiment at very low temperatures. And so we plan to build both gate-based quantum computer as well as a quantum annealer. And we, in addition to quantum computing, we're also planning to do experiments on quantum sensing. And we have decided to work on 3 different platforms: photonic integrated circuits, nitrogen vacancy centers, and ultra-cold atoms. Well, I have rushed through this because you'll be hearing talks, or at least presentations on these topics by the experimentalists who are working on these areas. Okay, now I think we can move on to the last slide, which would be of interest to all the students, is that we are a center that's dedicated to both research and education, as I mentioned earlier. So we started a PhD program in 2022 in collaboration with IIT Tirupati, and that is still continuing. And last year, in 2023, we have also signed an agreement with the Academy of Scientific and Innovative Research, which is part of CSIR. And we will be giving our PhDs from both these institutes, that is IIT Tirupati as well as ACSIR. As I said, ACSIR is a part of CSIR. It's like a deemed university that can give degrees. Now, the focus is on training students in frontier areas of quantum computing, quantum information science, which includes quantum communication, quantum sensing, and also applications of quantum materials to quantum technologies. And for this, coursework is absolutely necessary. So we teach courses related to these areas. And we also will be offering projects, hands-on projects in these areas. And currently we have 10 PhD students, including one foreign student from Cameroon. And we expect many more students to join in the coming years. We organize special lectures, workshops, webinars on topics that are of current interest in quantum computation, quantum information, quantum sensing, and related areas. And these are done on a regular basis. We have both seminars and lectures, and we plan to continue with this program in the future. So that is all that I have to say. And now I'll request the next faculty member to make the presentation.
Thank you, Professor Das. So I'd request Professor
You
Dev.
need a permission to share screen, right?
Yes, yes. You are now a co-host, so you can share your screen.
Okay. Do you see my screen now?
Yes, yes. We are able to see your screen now.
Okay. So I go to where? How do I make this pictures panel smaller?
I think you can press the escape key. And so if you're on full screen, then it will take you out of the full screen.
No, I'm going out of the full screen.
I see.
Not going out of the full screen. Well, anyway, it's coming back. This on the right side, I have a window that shows all the pictures. All of us.
Of the participants who are in the Zoom meeting?
No. I see my picture, Bhanu's picture, Devashi's picture.
Right. Those of you who have your video on, I think it shows your pictures on the right panel. Oh, do you want that to go away?
Yeah, because it is covering the screen.
Okay. That's only on your computer. For others, rest of us are able to see your full screen without that panel. But to get rid of the panel, if you go to the top, there would be this one rectangle, two rectangles, four rectangles and all. So if you click on the one rectangle, only the speakers view would be visible.
Is this the one?
We can't see what's happening on your screen, unfortunately.
Oh.
We can only see your slides.
Yeah. Did it go away?
Okay, can you see me there or not?
Yes, we can see you and we can also see the screen.
Okay, so then I can probably slide this little box on the right. Okay, fine.
I see. Okay.
So let me introduce first myself. My name is Bhupendranath Dev. I'm a professor at the center here. And I am actually, and my group is actually developing a superconducting quantum computer, as Professor Bhanu Das has mentioned. So I'll just introduce you to what we are doing here briefly. It's a quantum computing and fundamental research with superconducting qubits. Many of you have heard probably in 2019, Google announced quantum supremacy. What they have done, they have at that time, they had a 54-qubit quantum processor, or the quantum computer. They used that computer to carry out a calculation in 200 seconds. And they estimated that the same calculation would have taken even the best classical supercomputer 10,000 years to complete, which in other words, which was impossible with any classical supercomputer. So that just briefly gives you an idea about the power of quantum computers. Now the superconducting qubits or the superconducting processors are to be kept at an extremely low temperature. That's about 10 millikelvin, that's what's shown here, for them to function. And a superconducting qubit is essentially an LC circuit built with a superconducting material. As you see here, is a capacitor and an inductor. What happens here, the charge flow happens in opposite directions in a periodic manner. And in undergraduate classes, you have learned about harmonic oscillators, classical, and then in postgraduate, you probably learned the quantum harmonic oscillators also. So this is basically an harmonic oscillator made with superconducting materials. Now the harmonic oscillator, if you take that, you know that this potential is of this form, and the quantum harmonic oscillator has energy levels with the same spacing between all consecutive levels. And this is not suitable for a quantum beat using superconductors because this energy level separation equal causes some problems. Now, if you use, instead of an ordinary inductor, a different kind of inductor, which is built with a Josephson junction, then this can provide potential which deviates from the simple harmonic potential. So this is an anharmonic potential. And within that, the energy level separations are different. And this is what is ideal for making a superconducting qubit with an LC circuit with L represented by a nonlinear inductor that is built with a Josephson junction. Now, what is a Josephson junction? This is, if you have a superconducting material, two different superconducting materials on two sides, and in between you have a spacer of insulator, then what happens in such a structure, if you are passing electron or passing a current through it, an electron can tunnel through the insulating barrier from one side to the other. But if you use a superconductor, there your carrier is not a single electron, it's a Cooper pair. So in this case, the Cooper pairs can tunnel from one superconductor to another superconductor. And when this is integrated inside your LC oscillator, it produces that anharmonic potential and the required energy spacing for the superconducting qubit. So the primary component of a superconducting qubit is a Josephson junction, which are fabricated in this structure between two superconducting films, one insulating layer. That is very thin, actually. The insulating layer is about 2 nanometer thickness. So that Cooper pair tunneling can occur through this thin insulating layer. And this is our dilution refrigerator, which you need for your superconducting quantum computer. And this is 10 millikelvin, which is minus 273.14 degrees Celsius. And this is absolute zero, is minus 273.15 degrees Celsius. So this temperature is just about 0.01 degrees Celsius above the absolute zero temperature. As you see this can, if you take inside this vacuum, and if you open this up, take 4 layers, this can, and next layer, next layer, then you see this is what is inside. And outside the temperature is, of course, 300 Kelvin. And gradually at different stages, the temperature is reduced. And at the bottom here, the temperature is 10 millikelvin. And this is, at this condition, you have to keep your quantum processor, or the superconducting quantum processor. As you see here, this is a bare dilution refrigerator, as you see. And later, we have integrated the electronic components which function at low temperature. That's why it's called the cryogenic or cryo-electronic components. And that has been integrated within the dilution refrigerator. Now, if you look at this one, at the top, there is something as you see here. So for controlling the qubits, which are bottom down here, you need to send some signals from outside electronics. And that is also those electronic modules are on this rack, qubit control and manipulation electronic modules. So with these components, now if you put in your superconducting qubits at the place where the temperature is 10 millikelvin, you are ready to work with your quantum computer. So initially it's going to be with one superconducting qubit. Later on, we'll expand to a larger number of qubits with that. Now, what basic science research one can carry out with superconducting qubits, I'll just try to give a glimpse of that. You know that if you have a hydrogen atom, it has energy level, so 1s level at minus 13.6 eV below zero. So if there are two hydrogen atoms far away, so their energy levels are at the same value. Now imagine that you are trying to measure the energy levels of this one, and as this one is approaching this hydrogen atom, what will happen? Eventually, what you have, it forms a bond, and the energy levels are different. The initial energy levels are somewhere in the middle of that, and they split into two. So that's the signature of that interaction. Quantum interaction is taking place. So that means if you do not see the other side, what is happening, you don't have to see it. If you just measure on this side, sitting on this side, how the energy level is changing, you can actually determine the level of interaction between two atoms. Now, superconducting quantum beat is like a superatom. So this also has energy levels like this hydrogen atom. And we work with two-level systems here. So if one of them, say this hydrogen atom, is a superatom like a superconducting qubit, you can in principle study the interaction between these two. Now you can do it in many different ways, like light matter interaction. In this case, we show that microwave cavity and qubit. So this shows that this structure, this groove is a cavity. Within that, you can set a microwave guide with a particular frequency of microwave photons, and here is a qubit. So their interaction you can study. And how do you do that? As I said, if you can look at one of them, so we can look at either the qubit, what is happening to the qubit, or you can look at the frequency of these photons in the cavity, microwave photon. So let's see what happens. Say omega r is the frequency of the cavity photon, and due to the photon qubit interaction, omega r shifts to omega r plus delta omega. That means it shifts to a slightly higher frequency when the qubit is at the lower energy state, so zero state. Or omega r shift to slightly lower frequency when the qubit is at state 1. So what does it tell us? That if we measure the frequency of this cavity and we find that it has shifted to this value, then we know that the qubit is at zero state. So that means we can determine the state of the qubit. So either we can look at the qubit, changes in the qubit, or changes in the frequency. We can extend it a little more. So for example, if you have a cavity, which I have just shown, and the qubit, these two I have shown, but if you have, say, magnetic balls inside the cavity also, then you can actually control the magnon, but the magnetic excitation in that. Then you can study this interaction, as well as this interaction. So different kinds of fundamental quantum mechanical interactions you can follow. And in this picture, it shows this is the cavity, and this is the qubit, and this is a magnetic ball, yttrium iron garnet ball. And the magnetic field you can apply with this through a coil, passing current through a coil. And that's how you can tune the magnon frequency. Say the cubic frequency is fixed and magnon frequency are changing. So what happens in this picture, if you look at, sorry. So here it shows the coil current. That means I'm increasing the magnetic field. So magnon frequency changing this way as a function of this field. and qubit is not affected by that, it's constant. When these two frequencies are far apart, there is very little interaction, so qubit frequency doesn't change much. As these two frequencies are coming closer and closer, qubit frequency gets shifted, and at this degeneracy of energy, and this is a maximum interaction, and the qubit frequency has shifted by a large amount. On this side, it's also this side. So this is how we can study the interaction strength between the qubit and the magnons. So this is how different kinds of fundamental science also you can pursue. So quantum computation as well as different kinds of fundamental science we can pursue with superconducting qubits. Now, we also explored the material science aspect for the coherence time of superconducting qubits. You know, the quantum system is fragile. This is your wave function of the quantum system, but it interacts with the environment and then it stays, gradually decay, and finally it is lost. So it is only useful when it remains in the good condition here. So your quantum calculation has to be finished before that. So obviously the intention is to enhance the lifetime for this state, which is called the coherence time. We are also carrying out some research in that direction on some materials with the prospect of enhancing the superconducting coherence time. So this is the material we are investigating at this moment. So these are the aspects we are carrying out with the superconducting qubit platform. That's all. Thank you.
Thank you, Professor Dev. I'll now request Dr. Tanmay to present his work.
Okay, thank you, Dr. Prasanna. Okay, am I audible?
Yes,
Okay.
you are.
Let me share the screen.
Okay. Yes, we are able to see your screen.
All right. Yes. So. Okay. I think as introduced by Professor Das during the introduction part, he has mentioned about the quantum computing activity as well as quantum sensing activity. So I am a part of quantum sensing activity at CQuERE, and in particular, I am working on photonic integrated circuits. So I will first start with what I mean by photonic integrated circuit. So basically, if you think, so we all have seen the circuits, electronic circuits particularly. Now, basically, if you can replace the electrons and you replace it with photons by some means, that becomes a photonic circuits. Now, integrated means you want to kind of miniaturize the whole circuit onto a smaller structure. Okay, it might be on chip or it can be in a slightly bigger platform. So basically, you want to assemble all the components of these circuits. For example, you need a router to route the photons. You need a source to start the photons or to generate the photons. And you need a detector to detect these photons that you are routing. So all these three main components, if you can assemble onto a single platform, a small platform, that becomes a photonic integrated circuit as a whole. Now, to be specific, from this photonic integrated circuit, there is a slight bifurcation started in 2008 when this photonic integrated circuit group started looking into a different avenue, and that is called integrated quantum photonics circuits, which means basically you are using the classical photonic circuits that you use on a regular basis in different applications for a transceiver circuit that you use for data processing in data centers. And then you couple the quantum nature of light. So, for example, if you are using, let's say, a photon with a single photon, and you couple it with a router or photonic circuit. Sometimes these photonic routers are called waveguides. So it's a very similar analogy that we all see during a fiber optic cable to transfer the data from one place to another. The same you can do on a miniaturized chip by using waveguides. So basically you are confining the light using total internal reflection property of light, and then you guide the light from one point to another. Okay, now so the field of quantum photonics started with coupling the NV centers. I will come to that, what I mean by NV centers. NV in particular is nitrogen vacancy centers, and you can find in different materials NV centers. For example, one of the common materials for NV is diamond. I will come to that later. So you couple these NVs to waveguides, and then you can route the photons coming out from NV centers, and you can send these single photons through these waveguides from one place to another. And by doing this, you can do multiple tasks. You can use it for different applications like sensing. You can use it for computing. You can use for other stuffs also, right? So after this, there are a kind of increase in the amount of works that started, and you can see it's gradually starting increasing. People have shown different properties of light on a single chip, starting from interference of light or single photons, then multi-photon interference, then different kind of computation property. And very recently in 2022, Xanadu, they have come up with their own photonic-based quantum computer, and that works on basically routing the photons and generating the photons on a single chip, and then process it at a quantum processor. Okay, so this is kind of overall roadmap, but this field still continues, because for quantum computation, we need more number of per qubits, and that has to be error-free as well. So there is now a race in order to get this error-free quantum computation. Okay. Now, in our group, we are working mainly in 3 areas in particular. So you can look in this image on the right side, and then so this is the kind of one example of one of the components of photonic integrated circuit. So this is called an interferometer. It's called Mach-Zehnder interferometer, which has 2 ports, 2 output ports and 2 input ports, and you can guide light from either of these 2 input ports, and you can detect the light from the other components. Now, in this whole schematic, there are red marked words, which means that we are working in these 3 domains mainly. So this circuit is a general circuit. You can use it for different applications, but here in CQuERE, we are mainly targeting 2 aspects. One is you can use it for NV center-based quantum magnetometry. Then you can use it for quantum light generation. By light generation, I mean you can use integrated photonics to route single photons from a source, and then quantum sensing, which I will come a bit later. Okay, so some of the goals that we want to achieve with these photonic integrated circuits is mainly with basically this structure that I have shown here. We want to use this for quantum enhanced sensing. I'll come to that, what I mean by quantum enhanced sensing. And then we are also working in different kind of single photon emissions, that is quantum light source, from different materials. One of them is diamond. And also we are working on nitrogen vacancy centers, which I will explain in coming slides. Okay, so these are our primary goals. Now, to start with, the first component that we are working on at present is called on-chip Mach-Zehnder interferometer. This is one of the basic components for photonic integrated circuits. And if you can use it, if you can actually fabricate this circuit, you can actually, or this component, you can use it for multiple applications in photonics. Now, the basic structure that we are adapting is basically very simple. It's basically a single input light source, you can see from this schematic. And then you have a Y splitter or a Y branch, which splits the lights. It's like a beam splitter operation that you do in bulk optics. And then you route that light in 2 arms, and then again it combines, and then you get the output. Now, these two arms that I just talked about, one of the arm is called reference arm, another arm is sensing arm. And the preliminary study that we are working on right now is to use basically this structure to sense a very specific amount of elements into a solution or into a gas. So by using this kind of architecture, you can use you can use this architecture for sensing application. And if you use, so I didn't mention about this particular input light part. So input light can be used as a laser source. So that means you are still in the classical domain. But if you replace this input light with a quantum light source, that means a single photon source or an entangled photon source, then you can actually increase the sensitivity. Now, I was talking about this sensitivity. How do you detect this sensitivity? Basically, what you can do, you can measure this output or the intensity of the light on your photodetector, and this intensity of light will give you information about the phase. So if you have a sensing material at this sensing arm, so this sensing material will cause a slight change in the refractive index of this arm because of this evanescent field coupling, and that can lead to a very nominal change in the phase, and that can be picked up from the intensity profile. So that's what we are studying now. So here are some lists that we are aiming to use this architecture. Mainly, we are using single silicon-based architecture. Silicon, so these waveguides are silicon or silicon nitride. You can buy these wafers and you can fabricate using traditional lithography processes. I'll just show what we have fabricated recently. So this is a top view image of same structure that you see on the left. And then you see this from one port, you can put light, and then you can guide the light and you can detect it in the other side. So this structure, you can am I audible? Hello?
Yes, you're audible.
Okay.
Yes.
So this structure the dimension of the structures, the end to end is about 1 millimeter, and the width of these waveguides are about 2 micron. All right. Now, so this is kind of basic structure that we are aiming for a quantum sensing property. We are basically aiming to use Mach-Zehnder interferometer on chip to have a quantum enhanced sensitivity. So the other platform that I was talking about is color centers. Now, what do I mean by color centers is basically these are atomic scale defects into a lattice structure. It might be diamond, it can be any other materials also. So in nitrogen vacancy centers, what it happens, you have a nitrogen atom, you substitute, so in diamond lattice particularly, you have carbon atoms there, and then you replace one of the carbon atoms with nitrogen. There are different ways by which you can replace one of these carbon atom. And then you also create an adjacent vacancy center, adjacent vacancy in this lattice. And at specific condition, if you can give this system a good condition, then it will form a bound structure, and then you call is that it calls as a it is called as a nitrogen vacancy center. And then you can have a kind of artificial atom-like structure where you have discrete energy levels. Now, what do I mean by discrete energy levels? You have for nitrogen vacancy centers in diamond, you have this ground state, and you have a excited state, whereas you have also a singlet state here. Okay. Now, if you excite, basically, so this ground state, in general cases, it is a triplet state. If you don't put a microwave radiation, then this plus minus 1 state is actually degenerate. So when you excite with a 532 nanometer green laser, so you have kind of excitation of these electrons, which goes to the excited states, and it comes back. This this path or the direct path is actually radiative path. So you get in turn radiation of about generally it is about 637 nanometer, that is in red region. So you basically you can detect this using a spectrometer easily. Now there is another pathway which these electrons can follow also, and you can there is a singlet state which is available, and you then the electrons, the excited electrons, can come down to this singlet state and then comes back to this ground state. But this pathway is not radiative. It's a non-radiative pathway, so you don't get any emission out of it, right? So this is the property that is specifically used for a magnetometry application. So what you do generally in case of normal cases, when you don't have, let's say, any external magnetic field, you pump this this NV center with green laser and initialize the whole initialize the atoms at ground state. So that's how you prepare the sample, and then you use different kind of laser pulses to manipulate the states. So what you generate generally, or in your detector, what you get basically is a photoluminescence or fluorescence that you are detecting. And in case of a degenerate state, you get a single peak which is specific to a particular microwave frequency, that is 2.87 gigahertz normally. And if you can with the external magnetic field, if you lift off this degeneracy by Zeeman effect, then you can actually split these two peaks or the deeps into two. So the single deep can be split into two, and these peak positions or the separation between these two peaks will give you the information about the external magnetic field that you are applying. So basically, it's all about initializing the state or preparing the state at zero ground state, and then you put external magnetic field, and basically you see this splitting, right? So what is the current scenario? If you look in this graph, basically there are multiple magnetometers that are available at present. And you can have superconducting squid-based magnetometer. You can have vapor cell, hot vapor cells, and also you can have Hall probe-based sensors. There are multiple. So you can have a kind of, you can plot this in two axes. One is you can have sensitivity and then the resolution. The resolution, spatial resolution, that means how small, how close you can go when you are measuring this magnetic field. And the sensitivity is, of course, how small magnetic field you are sensing. So there is a trade-off. If you look in the current scenario, there is a trade-off. So thus the whole magnetic magnetometers that are available at present. So though, for example, the vapor cell-based magnetometers, they have very high sensitivity, but their spatial resolution is restricted. Right. On the other hand, for diamond, you can go very high spatial resolution, or you can go to very small value or very close to the surface, but your sensitivity is still low. So there is now the whole research field is looking for kind of a holy grail where you can see this gold part in red circle kind of thing. So this is the holy grail, and you can. So people are working to have a very high sensitivity with very high spatial resolution. So we are working in this direction. So our present scenario is that we are setting up our labs. So we are working on mainly, so this is kind of layout that we are following. We have a part of which is used for a single photon detection. So the same circuit you can use for single photon detection, which is used for integrated photonics part. And there is a beam splitter which gives for magnetometry application using diamonds, right? Okay. So in summary, we are working in these areas, which covers mainly the magnetometry using NV centers in diamond. We want to achieve very high sensitivity. We want to couple mainly photonic integrated circuits with NV diamonds, basically to use to enhance the sensitivity. So there are certain bottlenecks that can be overcome by using the photonic integrated circuit architecture for diamonds. Then we are also working on quantum enhanced sensing using this Mach-Zehnder interferometer assembly on chip. And then we are also working on single photon emitters, and NV is one of them, one of the single photon emitters. But there are still bottlenecks to have a kind of room temperature single photon emitter. These single photon emitters are very important, particularly with quantum computation and quantum information processing or quantum communication. With this, some of the collaborators are mentioned here, and that's all from my side. Thank you very much.
Thank you very much, Dr. Tanmay. I now request Dr. Oishik to present his works.
Rishik may not have heard it, maybe.
Yeah. I'm just
Okay,
trying to
sure.
upload. Somehow I'm not getting the upload. Yeah. Is my screen visible?
Not
Was.
yet.
Yeah,
Now
yes, it has come.
Great. So hi, good afternoon, everyone, and welcome to our outreach program. So we are working on quantum sensing, as my previous speaker, my colleague Dr. Tanmay Basu told, and also Professor Das mentioned. So I am working on cold atom-based platform for quantum sensing applications at CQuERE. So basically, this is a brief schematic, you can say, for the secure roadmap based on neutral atom-based platform. So the initial target is to develop the absolute quantum gravimeter. What is this and how it will work, I will tell in my future slides. So if you see the effect of tides or the gravitational field, you can actually see a huge gradient of the acceleration due to gravity across the surface of our Earth. And not only over the surface, even like in case of microgravity also, you can measure very precisely the gravitational field. So basically, the Earth's gravity field gives you a precise, it can give you a precise position or your accuracy. As you know, this Earth is not like over a sphere completely, and basically, due to the centrifugal forces and also the gravitational field gets changed. So the idea is to measure the gravity very precisely so that we can actually map the gravity field, and that gives us a lot of information like this. So if you can measure the g, small g, very precisely, so each decimal of your gravitation, this g, gives you information based on the latitude variation and elevation, and then terrain effect due to the tidal effects, and also the density variations of our underneath all these informations. And all these informations you can measure if you have such a precision to measure the G. And broadly, if we say the application areas is mostly geophysical research areas, where you can actually map or model different parameters, volcanic eruptions, and then earthquake detection, seismology. Also, you can have its application in the inertial navigation, environmental monitoring, also the exploration in terms of oil and minerals. So, what it is? Basically, with the invention of laser cooling, it enables lots of promises in the basic physics research. And people already have invented that using atom interferometry, where you use atoms instead of lights, you can precisely measure the path length difference. And that actually can give you different physical parameters which you want to measure. In our application, we are intend to measure the acceleration due to gravity in the vertical direction. So for that, what we do, we simply laser cool the atoms. By laser cooling, in layman's language, we can say that we can basically bring the atoms in a localized or in a stationary form, so that we can bring their random motions as low as possible. So from a few hundreds of meters per second, we used to bring them down to few centimeters per second. So they are very much localized. So now then we drop them, and the experiment is done under free fall condition. So while you dropping it, we use laser pulses to mimic the interferometer sequences, like the reflection and the combining. So since the overall atoms traverse like light in two different paths, if there is any phase difference involved in the paths, so that is results as a interference fringe. So in this diagram, this is the basic block diagram of a cold atom gravimeter, what we are working on at present. So we basically laser cool atoms in a three-dimensional optical mode, and then we'll drop it. And while dropping, we do the interferometry. And by saying the interferometry, basically we split that population, and then we reverse their population, and finally we combine their population. So in terms of atom interferometry, and finally we do the detection. By symmetric detection, actually you can measure the phase difference between these two balls that actually experience during their trajectory. And that actually gives you the exact phase relation, or rather to say the small g value. So the target accuracy, what I'm talking about out of this kind of a measurement system, is of the order of some nano g. So at present, we just started our activity 1 year back, and at present we have established lab, and then we really moving forward. And this is the CAD drawing of the tabletop setup, what we have planned and designed. So this is now in place. So we are preparing the ultra vacuum, because the entire experiment has to be done inside the ultra vacuum chamber. And these are some further details of the operations and block diagrams related to the lasers and all these things. So I would like to mention here one broad thing, that the basic equipment, or rather to say the measurement system, consists of three basic building blocks. One is the physics package or sensor head. Another one is the detailed optical setup, where you generate the precise laser frequencies to interrogate the atoms and atoms, and then you detect them. And on top of that, you have a full-fledged control electronics to control the entire operation, because the operation is kind of sequential. So you cool it, then drop it, then detect it. Then again you cool it and then drop it and then detect it. Like this way, the whole sequence goes on. So, and in order to complete all these processes, several sub-processes are involved in this, and they take part in that overall experimental process. So now if we see the worldwide scenario, so this is a span of over 15 years. So we had a laboratory prototype, and then people have moved from a laboratory prototype to a transportable one. But as you see, it is yet bulky. So then further development is going on, and then it has been further miniaturized and commercialized, but still it is not field deployable. So in that area, further research is going on. So there are like plenty of research scopes from the point of view, like you can do it from engineering aspect, you can do from physics aspect to in this area, and it has a drastic implementation in the day-to-day life of let's say when if you want to do some like navigate inertial using some inertial system, these guys can play up a significant role, and if we can significantly miniaturize the whole physics package and system. So research is going on in that direction, and also we are focusing in the same direction. So at present, we have a very small team. So one PhD student, one postdoc, and 2 project assistants are working in this area. So we have a state-of-art equipments and laboratory facilities related to all the subsystem developments like ultra-high vacuums, optics, optomechanics, optoelectronics, and others. And the overall goal for this research is to make the entire setup a transportable one, so that we can do some physical measurement which has a real life implementation. And also along on the path of this development, we have like target to generate trained manpower as well as quantum literacy. Before ending, I just want to give you a brief overview or market overview, rather to say. So there are not many players across the globe who are involved specifically in this area, and it has a very potential growth opportunity. So thank you so much. And of course, we are looking for students, PhDs and postdocs.
Thank you very much, Dr. Roishik. So now that you have finished looking at the experimental activities in a center, quantum computing as well as quantum sensing, we can now move to the theory segments. We'll first begin by discussing quantum information and communication activities at a center. And I request Professor Pati to take over. Thank you.
Yeah, so let me try to share my screen. Can you see now?
Yes, we are able to see your screen.
Okay, so myself, Arun Pati, recently I joined CQuERE. So I have been working in quantum information and quantum computation, quantum communication for almost more than 35 years now. And my research topics are quite, wide variety. Sometimes to do with quantum communication, sometimes quantum information basics and quantum computing also. So today I will try to highlight some of our current interest. So one of the interesting thing that our group has been doing over the last several years is trying to prove new kind of uncertainty relations, which are much more stronger than what you know in your MSc textbook. In MSc, what you learn is the typical Heisenberg uncertainty relation or Heisenberg-Robertson Schrodinger relation and things like that. But we have proved a stronger uncertainty relation that goes beyond Heisenberg, in the sense that the Heisenberg relation is a special case of our new relation. And this uncertainty relation is one of the cornerstone of quantum mechanics and quantum information. It has a lot of applications, starting from finding new quantum speed limits, which I will try to explain a little bit more, and something to do with recent work that I did, quantum acceleration limit, and it has a lot of application in quantum technology, and also in entanglement detection, quantum key distribution, and many more things. Not only that, this kind of uncertainty relation play a very important role in testing some of the fundamental predictions of quantum mechanics also. Quantum speed limit is something which has attracted a lot of attention over the last 5 to 10 years. Though this was initially investigated by Mandelstam and Tom in 1945, but over the last 10 years, several groups are working on this quantum speed limit, because it is so basic, so fundamental, that it has application not only in quantum mechanics, it has also application in quantum computing, quantum control, quantum thermodynamics, and many more things. So the basic question you ask in this context is the following. You are given some initial state and you are given a final state. Your goal is to reach from the initial state to the final state by applying some suitable Hamiltonian. And obviously, you would like to reach your final state in a shorter time. So how long it takes for the system to evolve from this initial state to the final state? So this question is answered by quantum speed limit. And that gives a lower bound to time that the system will take in reaching from the initial state to the final state. So how does this behave? It behaves essentially depends on the shortest path that connects the initial and final point, and also on the fluctuation in the Hamiltonian. And as you know, in quantum mechanics, if you're given two state vectors like initial state and final state, there are actually infinite number of Hamiltonian which can connect these 2 points, But the biggest goal here is to find the optimal Hamiltonian which will drive the system along the shortest path. If you go along the shortest path, obviously you will reach in a shorter time. So that is the main goal you would like to achieve. So this quantum speed limit essentially depends on these two things, that is the shortest path and the fluctuation in the Hamiltonian. And over last, over last 5 to 7 years, many of my previous students have been working on this quantum speed limit, trying to find tighter bounds and trying to apply for open quantum system, and also apply in the context of quantum thermodynamics and arbitrary time continuous evolution, in the sense that you don't need any particular dynamics like Schrodinger evolution or Krauss operator formalism on any open system dynamics. Any equation that will, in fact, you don't need any equation to to detect this, to obtain this speed limit. All you need is that you need a state vector for the system. It should evolve continuously in time. So it can go beyond even quantum mechanics also, And very recently, we have proved something to do with exact speed limit, because that is often very interesting, because that will, if you can estimate the exact bound, you don't have to deal with the empty bound, the so-called Mandelstam bound and other bounds, because you know exactly how much time the system will take from the initial state to final state. And as I mentioned in the beginning, one of the recent things we did is we can define, once you define a speed of a quantum system, and by the way, this speed is not the speed that you are familiar in your ordinary Euclidean space. This is the speed of the quantum system on the quantum state space. but that is a technical thing. I don't want to go into detail of that. But essentially, this is the speed of the quantum system defined on the state space. Essentially, the state lives in Hilbert space, and then you define so-called a projective Hilbert space on which your system actually lives, and on that system evolves. So you can define a speed, but if you can define a speed, the next thing is you can also define an acceleration, essentially taking the derivative of the speed. And recently we did something, and that has a lot of application in adiabatic quantum computing, and even shortcut to adiabaticity and things like that. Okay, so another direction that our group has been exploring is to do with weak measurement. Typically, what you learn in your MSc days is that when you do a measurement, you are bound to get one of the eigenvalue of the observable that you're trying to measure is a result of the measurement. But in late 80s and early 90s, Arnov and Weidman, they tried to propose a new idea called weak measurement. So what they do is they weakly couple the system and the apparatus that the system is trying to, that is trying to measure the system, and then you do a measurement on the system state. Depending on that particular outcome, which is called post-selection, you will see that the apparatus wave function will shift by something which is very strange. Strange in the sense that that quantity can be complex in nature. That means it can be real, it can be imaginary, it can be arbitrarily large also. And this strange result is the essential weak value. And this is a lot of applications starting from quantum metrology, quantum sensing, and even amplifying weak signal and sequential quantum communication, quantum foundation, and many more things. So again, this is very active area of research. And I don't know if some of you are familiar, so-called quantum chess arcade, where you can actually design an experimental setup where you send a particle through a Mach-Zehnder interferometer. By suitably designing this weak measurement, you can separate out the particle from its property. That is, particle will go through one path of the interferometer, whereas its spin or its polarization can go through another path. So you can actually dismantle the attribute of a particle from the particle itself. So very recently, actually, I heard last week they have a paper where actually they could also separate out using this weak measurement idea. They could actually separate the particle from its mass. So particle is at one place, whereas its mass at a different place. This is completely weird, completely counterintuitive, but that happens, quantum mechanics. Quantum mechanics is really weird, and you have to appreciate that. And our group also working on open quantum system. This is again very wide topic. Essentially, you have a system. As long as you don't allow any interaction with the external world, system evolves by unitary, by Schrodinger evolution. But once you start interacting your system with the external world, then this is no longer, described by Schrodinger equation. You need something to do with open system dynamics, which is often called Krauss operator formalism, and that you need to describe your system evolution. And this is very useful in quantum computing, quantum information, quantum communication, when you subject your system to noise. And often what we study is we study the fidelity of quantum information of a noisy channel, and also we try to preserve quantum coherence or quantum entanglement on the noisy channel. To do all this, you need to have a good understanding of open quantum system. Okay, I think this is all I wanted to say, but there are many more things our group has been working. So yeah. So I finished now.
Yeah. Thank you very much, Professor Pati.
Yes.
I now request Professor Pankaj Agrawal to speak about his works.
Okay. Can you see my screen?
Yes, yes.
Okay. Okay, so my name is Pankaj Agrawal. I also have joined recently this security TCG Crest, and my broad area of interest is quantum information and communication. And this short presentation is aimed at students, and to introduce them to one area of research which they may find interesting. And to introduce this area, I would refer to the Nobel Prize, which was given in 2022. Okay. So Nobel Prize in 2022 was awarded to Alan Aspect, John Clauser, and Anton Zellinger. Okay. And citation said, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So in particular, their pamphlet said the Nobel Prize in Physics this year recognizes efforts to take quantum weirdness out of philosophical discussion and to experimental demonstration and some practical applications. So this prize recognized that a work which started in the domain of, you may say, to explore the quantum weirdness, and then it was found that that exploration led to some applications, practical applications, in particular in the field of communication. So actually this prize recognized the work on the testing of Bell inequalities, as well as demonstrating some of the communication protocol, in particular entanglement swapping. So this prize recognized work on, Bell inequalities as well as quantum communication. So this is one of the theme on which there is some of the work is being done in our center. Okay, so question is this referred to this Nobel Prize citation even refers to weirdness, right? And I think any student who comes to quantum mechanics for the first time is always sometime puzzled. Okay, so if you are puzzled, that you are in a good company. Okay, as you know, two of the pioneers of quantum mechanics are Niels Bohr and later, Richard Feynman, who gave a different way to do quantum mechanics. So both of them also found quantum mechanics weird. So it is not, and they also found that it can make them uncomfortable. Okay, so like Niels Bohr, not shocked when they first come across quantum theory, cannot possibly have understood it. So if you are, confused, then you are in a good company. Even Feynman, when he was somewhat old, he said, at least, okay, that we always have had a great deal of difficulties in understanding the world view that quantum mechanics represents. At least I do, because I am old enough man that I have not got to the point that this stuff is obvious to me. So he said in 1982, when he was, I think, almost 70, or at least late 60s. Okay. So quantum mechanics, people do find somewhat weird, but what makes it weird? Okay. So anyway, so from the Nobel Prize, what you see that there is a foundation, but then there is application. And study in foundations, they can be important for applications. So this is one of the ideas one can take, that foundation is important for applications. So thinking about what, if anything, is weird about quantum mechanics is not a waste of time. I mean, this Nobel Prize in 2022 also, underlines it. So one of the approach which sometimes is advocated, that shut up and calculate, though it has its own value, but foundational question, thinking about those questions is also valuable. And actually current excitement about new quantum technologies has its origin in foundational questions. And so there are things which you can do using quantum mechanical resources that are not possible if you use classical resources. Then what do I mean by quantum mechanical resources, right? So you will find that these resources, they lie in this what people refer to mysterious aspects of quantum mechanics. And these resources, at the heart of that is what is known as superposition. So I think people have talked many times in these presentations about a qubit. And let me start with one slide just to introduce you to what qubit is and how it leads to discussion of entanglement. Then it further leads to discussion in quantum communication and weirdness of quantum mechanics and all that. So a qubit, as people have talked many times today, and some of you may know also, it can be thought of as a two-state system. So it is a system which can be in two different states, or is sometimes a state vector of a system of a two-state system. Now, if you had a classical system, okay, you can characterize a state. If it is a two-state classical system, you can characterize the state by say two numbers, say 0 and 1. But this system can be in either 0 or 1. But if it is a quantum system, it can exist in a what is known as a linear superposition of these two states also. So a state could be say alpha 0 plus beta 1. So this is where you see quantum mechanics weirdness will starting to come. Okay, so state of a qubit is a vector in two-dimensional Hilbert space. Okay, and if you look at this state, if you make a measurement in computational basis, which is called 0 and 1 basis, you will find sometimes state is in, you will find on measurement probability, alpha mod square, that state is in, state of system is 0. And with mod beta square, state of system is 1. And if it's some other basis, then you will find some other states. Okay, so this is what makes it weird, okay, in some sense. But beyond it, this superposition, when you have a composite system, it leads to a puzzling property called entanglement. And this is an entanglement which is at the heart of current excitement about quantum technology. Okay, so just to, in one slide, just to tell you about entanglement. So if you have a composite system, right? So it means you have a more than one qubit system. Then you can write as a state as what you say direct product of a two state of the system A, a state of system B. Okay, so if you make a measurement in the first case, you will find that the state of system A is in 0 and state of system B is 1. But this system can exist in a state which is superposed state of two qubits, alpha 0, 1 plus beta 1, 0. Now, if you make a measurement on system A, sometime we'll find that system A is in a state 0 and sometime we'll find it in state 1. Okay. So, so this is where, such a state is called an entangled state. And more technically, if you want to define an entangled state, you will say that, okay, there is also notion of pure and mixed state, which I am not going into. The pure state is, you say, is entangled state if it cannot be written as a product state of subsystem. That is, if you have a system AB, you cannot write as a state as a system of A and with a tensor product of state of system B. Okay. Now, this may appear very simple, but as you go beyond 2-qubit pure state, these entangled state becomes very complex and you don't understand them even as soon as you go beyond 2-qubit pure state. So you may think you understand quantum mechanics, all you have to do is solve Schrodinger equation and all that, but you don't understand even very simple systems. So if you look at a system which is made up of just say 3 qubits or even a 2-qubit mixed state, there are many features of these systems which you don't understand, in particular like entanglement. I mean, there are quote unquote non-local features of these systems. There is still a lot to be done in these areas, and some of the work which is being done here is also in these areas. Try to understand multipartite and mixed state, their entanglement properties, and how to characterize them. Okay, how to understand them. Okay, so as I just mentioned a while ago, that this entanglement, use of entanglement has led to what sometimes people call second quantum revolution. So this revolution also involves asking many questions. Okay, so once there is entanglement, okay, state can be entangled. So these are some of the questions for which we still have no definite answers as soon as you go beyond a simple 2-qubit pure state. Okay, so like question you may want to ask, how much is the entanglement in a given state, right? This is one of the most basic question you may want to ask. And then you may want to ask, okay, if you have entangled state, what I can use it for, right? Yeah, if you are given a two different state, can I say state A is more entangled than the state B? Are more entangled state always more useful? Or even more elementary question is, if you are given a quantum state, can I say that this particular state is entangled? All these questions, which may sound simple, as soon as you go beyond 2-qubit pure state, they are difficult questions to answer. These answers depend, as you may say, on many things. System is a pure state, mixed state, bipartite, multipartite, qubit or high dimensional. But beyond 2-qubit pure state, these questions are not always easy to answer or even formulate properly. Okay, so most of these and similar theoretical questions have technological ramifications. A better understanding of entanglement, as well as using it as a resource to do things which you cannot do classically, it has led to what you call the second quantum revolution. So our group here is interested, in all these questions. So one of the part of the theme, as you saw in Nobel Prize, was Bell inequalities. So which is gives rise to what people call, which is sort of characterizing what people may call quantum non-locality. So these are people, Einstein, Podolsky, and Rosen. So like this Nobel Prize citation said, in 1935, these three people asked a foundational question, which has nothing to do. As can a quantum mechanical description of physical reality be considered complete? Now, this question led to a chain of events, which after 50 years led to what you may call second quantum revolution. So foundational question, which may seem irrelevant to practical application at a given time, may found application, say, a few decades down the road. So just to mention very briefly, in one slide, what sometimes people talk about is Bell inequality, and in whichever group here is also interested. So one of the simplest case which were tested, for which Nobel Prize was given for testing this particular inequality, it refers to two parties. You have two parties, say Alice and Bob. Alice can measure two observable, A1 and A2, which can have two outcomes, +1 and -1. Similarly, Bob can make measurement of two observables, both of which can have two outcomes, +1 and -1. So this is the simplest scenario which you could have. Very soon, scenarios can become very complicated, and a lot of research work is going on those complicated scenarios. And our group is also interested in those scenarios. So in this particular case, you can construct a combination of these observables. And once you find the expectation value or average value of those observables, it was found that if you believe in what Einstein believed in, what is known as local realism, then this inequality, so you will get an inequality that average of this combination of operators has to be equal to and less than 2. But these group of experimentalists who got the Nobel Prize, they showed that this inequality is actually violated. And this underlines the fact that quantum mechanics or quantum mechanical formalism is not a local reality. This is what was done by this group of people who got Nobel Prize, but they also demonstrated a quantum communication protocol. And this quantum communication protocol, which has importance in it could revolutionize our daily lives. Okay, so what is the heart of this quantum communication? It is either, you will say, single system in superposed state, or multi-qubit systems, multipartite system, which are entangled. So that is the heart of these new quantum communication protocols. Okay, so study of this also entanglement, it became more popular because people found that, there are communication protocol, which are which can do more than what a classical communication protocol could do. So I think it was in long ago, actually, when people showed that there are certain protocols, simplest of that being teleportation, entanglement swapping, secret sharing, where actually quantum information is to be communicated from one party to another. So suppose there are two parties. In a simplest scenario, you will have just two parties, where one party, say Alice, wants to send some information to party B. Now this information can be quantum in the sense it can be some state of a quantum system, or it can be classical. But that classical information Alice may want to send by using quantum resources, means this superposition, okay, and which can be characterized by something called coherence, okay. So communication, so these earliest protocol, they used some very particular type of states as resource and only two parties. But as you have more parties, you have more complicated states, things become again a bit complicated. And one of the problem actually in general in quantum communication is that when you want to send a quantum system, it has to go through some channel, and its interaction with that channel will introduce noise. And if you store even that a quantum system, it will still interact with the surroundings. And again, some noise will be introduced in the state of the system. So whatever protocol were introduced in the beginning, they were very simple. Just two parties, you have a system in pure state, no noise and all that. But real life is a lot more complicated. So a lot of work is going on those areas. In particular, people try to use this area of research, which is there called quantum error corrections, to reduce the impact of noise. So this is also one of the areas which is of interest here. So I'm not going to go in details what exactly the simplest protocols are, but they are actually now part of, they are primitives for communication over a more complex, what people may call network. So in the teleportation, what one sender wants to do, send the unknown state of a quantum system to another party. Okay, in case Alice to Bob. So Alice wants to send the state of a photon to Bob. Okay, and Alice does not know what is the state of the photon. So what she does, she uses a entangled state to do it. So there is a whole protocol which she uses, few steps, and she is able to send this state of photon to receiver Bob. Okay, without actually sending her photon. She is going to use as a resource a 2-qubit state. So this is now, so here you are sending a quantum state from one party to another. So this is, you can say building block of more complex quantum communication systems. Another building block of a quantum communication system called quantum network is something called entanglement swapping. So here, if you have two parties, there are four parties. So one or two, they have entangled state, A and B, which are entangled state. If you make a certain type of measurement on party 2 and A make a certain type of measurement, then what happens is that this party 1 and B, who have never interacted, their system become entangled. So systems of party 1 and party B, system which have never interacted, they become entangled. So in this way, you can transfer entanglement, say from one set of system to another set of system. This is also plays an important role on a quantum network, because you want to swap a state between two parties to some other two parties. Okay. So another area of interest in quantum communication goes under the heading of quantum cryptography, basically secure quantum communication. So goal of this cryptography is to communicate information, say, in a very simplest scenario, from one party, say Alice to Bob, which is not being compromised by some intruder like Eve. So one of the way one does it, that Alice will encrypt her message by using some key called K. So she will use two things, one key and one encryption procedure. She will get a new message C called cipher. That message she sends to Bob. Then Bob again uses the key and a decryption procedure to get back the message. So one of the important thing in this whole process is making this key which is common to Alice and Bob. So making this key this is in a secure manner is one of the important part of what is known as quantum cryptography. Because here you want to do quantum key distribution without this key distribution being compromised by a third party called Eve. Okay, so these also, there are many, some of the simplest protocol you use against single particle, which is in superposed state or entangled state. So they were protocol introduced long ago. Actually, one of the first protocol was introduced in a conference in India, in Bangalore. Okay. But again, these are simplest scenarios, okay, where you have but very soon things become complicated. As you have more complicated systems, you have noise, you have, multi-parties. So, then you want to see whether that new protocol which you may want to introduce is secure. So protocol and security analysis of quantum key generation when many parties are involved is also an active area of research and also is of our interest. So as I just mentioned, this quantum network, so you want to go to a more complicated quantum communication setup. Okay, so we have as of now, we have a complex network of satellites and optical fiber for long distance classical communication. A simpler network of quantum communication is still a work in progress. In all communication protocol, one of the important issue that comes is distribution of entanglement over many nodes. How to do it efficiently? This is also an active area of research and in which we are also interested. And here, as I just mentioned, teleportation, entanglement, swapping, they act as primitives. So there are challenges because quantum resources are more fragile and quantum information cannot be copied. Okay, there is no cloning theorem, which plays a very important role in security analysis also, but it has, some positive as well as negative aspects. Of course, then there is noise. So work is needed both on theoretical front and experimental front. The world over, engineers, physicists are building devices for a quantum future. And so we have some interest in this quantum distribution of entanglement and also various communication protocol over this quantum network. So this future of this quantum future may come to India also through this National Quantum Mission. So, okay, so in this my last slide, I just want to mention that how communication is such an important part of this mission. So if you see the many points which are mentioned as the key objective of this mission, apart from building a quantum computer, okay, and also quantum sensing and developing quantum materials, so some of the important mission or some of the key objective relates to communication. So one of the key objective is to develop satellites-based secure quantum communication between two ground stations over a range of 2,000 kilometers within India, as well as long-distance secure quantum communication with other countries, or intercity QKD, quantum key distribution over 2,000 kilometers with trusted nodes using wavelength division multiplexing on existing optical fiber network. Beyond that, there is also one of the objectives is to build a multi-node quantum network with quantum memories, entanglement swapping, and synchronized quantum repeaters at each node. To achieve these goals would require collaboration of theoretical and experimental physicists and engineers in many domains. So anyone who may want to enter this area can look forward to exciting times. So our interest is in some of the theoretical aspects of this quantum secure communication and quantum non-locality, as well as how to characterize the quantum mechanical resources. Okay, thank you.
Thank you.
So I am done.
Okay, thank you very much, Professor Agrawal. I now request Professor Debashish Mukherjee to present.
Well, we are approaching the conclusion of the meeting today, and I won't take too much of the time because some of the most important things have already been discussed. I am really a theoretical chemist. I am the distinguished chair professor of CQuERE, and I had been active in quantum chemistry, which is essentially at the confluence of atomic and molecular physics, but it also contains something more, namely it also deals with what is much more difficult to deal, namely the organization and understanding of chemical reactions. With the advent of quantum mechanics, and particularly quantum many-body theory, the description of the atomic and molecular processes, including fragmentation of molecules into atoms, have taken a new turn because some of the many-body theories essentially promise to reduce the computational complexity and reducing the computational time, which was not available around the, let's say, even at the beginning of the 21st century. Now, when this offer came to me, I really got quite excited that I can learn new things, and I have been learning. And basically, I work in close collaboration with Professor Bhanu Das and Dr. Prasanna in the group. And basically, this is an activity comprising of quantum chemistry, atomic physics, and molecular physics. Essentially, what I have tried to do is to develop certain quantum algorithms by generating certain theoretical machinery, which have been found to be useful and interesting and sufficiently powerful to develop not only the description of electronic structure of molecules in the ground state, but also in their excited or ionized states. And one can think of certain methods in which a single method can actually tackle all these kind of three states. The challenge in quantum chemistry then translates while doing works using quantum computing methods is to find out suitable algorithms, quantum algorithms, which actually can do this rather difficult job. That's not trivial, and it is in the beginning. But already with the rather big quantum computers in the offing, certain other novel possibilities are, of course, in the offing. So I've been involved in that. And I have been involved not only for the ground state, but also of the excited or ionized states. For chemistry, the other important concept is, of course, chemical bonding and dissociation of molecules into atomic fragments. And this actually is based on a qualitative understanding of what are called the molecular potential energy curves. And in order to really have a good grounding of the good understanding as well as a good command of the potential energy curves in their lots of possibilities, separate potential energy curves, weakly avoided crossing of the potential energy curves, or strongly avoided crossings. These require, again, very, very highly correlated systems, which means that electrons repelling each other to try to repel each other. And if you do a poor job of really keeping them apart, then of course, the method will break down at the critical points. We have been roughly successful in some of the more complicated potential energy surface, but now then the challenge for us now essentially is to encompass these activities in the set of quantum algorithms. And that setting is slowly evolving, and hopefully it will unfold to yield things which have been considered earlier to be very, very intractable because of the difficulty of computation. So these are the things that is keeping me busy. And I'm learning quantum computing. At the same time, I'm trying to transcribe my old knowledges in the light of the new quantum computing strategy. And I think that is all. I mean, I didn't prepare any particular set of slides because essentially a lot of things that have to be done in the offing. So thanks a lot for your kind attention.
Thank you, Professor Mukherjee. I'll now share my screen and just expand a bit on what Professor Das and Professor Mukherjee spoke about the quantum computing theory group at CQuERE and the research activities that happen there. So are you able to see my screen?
Yes.
Okay, thank you.
Yeah.
Okay. So I'll first just begin by introducing our team, the quantum computing theory group team. So of course it's Professor Das, Professor Mukherjee. So both of them gave a nice overview of some aspects of the activities happening in our group. This is Professor Sugisaki, who's a visiting associate faculty at our center. This is of course me, and we have some postdocs, some visiting scientists, our quantum engineer that Professor Das was mentioning, our PhD students. This is Mr. Peniel, an international student from Cameroon who's working with us. And these are our future PhD students, and this is a project associate. So we have a nice team, a nice diverse team. And we also work on a variety of problems in the quantum computing theory group. There's quite a lot of detail in this slide, but I'll first begin with these two panels, where there could be some problems that are very hard in classical computing. So this is just a drawing that tells that, okay, you use classical computing where the units of information are bits. Then if you use the classical ways of processing on a computer, then there are some problems that are very hard. But on a quantum computer, when you go to quantum bits and there are analogous quantum gates and quantum circuits, then the problem becomes easy. But of course, the catch is that it's true only for specific problems. But the very nice thing is that atomic and molecular physics / quantum chemical calculations are one such set of problems. So as Professor Das and Professor Mukherjee mentioned, this is the main thrust area in the quantum computing theory group at our center. But we are also working on dynamics of physical systems. We have also made some preliminary progress on quantum algorithms for climate modeling and quantum algorithms for traffic flow control, which then becomes a real world application. I'll of course be talking for the rest of the talk on the atomic and molecular physics part, just to give some sort of a flavor of what's happening in our group. So again, as Professor Das mentioned, you can have gate-based as well as quantum annealer-based quantum computers. So we work on both fronts. And on the gate-based front, we work on both near-term algorithms as well as algorithms that have a more far-term outlook for the fault-tolerant quantum computing era. So for the former, we work with the variational quantum eigensolver, or the VQE algorithm, about which I'll briefly talk about. I'll also, of course, be talking about the HHL algorithm, named after the people who invented it, and also on the quantum annealer eigensolver algorithm. So we work on near-term and fault-tolerant error algorithms. We work on gate-based and quantum annealer-based frameworks. And typically, all of these topics involve devising or modifying quantum algorithms. And this really uses a lot of quantum mechanics and linear algebra that you learn in your master's. Then, of course, it involves developing programs to realize the algorithms. This involves software aspects. And then, of course, you need to execute on quantum hardware. So we have executed on quite a few quantum hardwares, and we also plan to work with quantum devices, for example, in the University of Wisconsin-Madison. Each of these devices are of a different type. For example, the IonQ is a trapped ion qubit quantum computer, whereas D-Wave is a superconducting qubit-based quantum computer, but used for quantum annealing. IBM, Rigetti, and the computer at University of Tokyo, these three are superconducting qubit quantum computers, and the one at Wisconsin-Madison is a device that uses cold atoms. So not only do we have quantum hardware, but a typical quantum hardware execution would also involve plenty of classical computing steps in terms of pre and post processing. So what you see here are basically the ingredients that go into working on all of these algorithms. So one would be a knowledge of quantum mechanics and linear algebra, and then of course some software, and then a combination of classical and quantum devices. So I'll very briefly talk about the first algorithm, the VQE algorithm. So you might be familiar with the Rayleigh-Ritz variational principle from your master's or earlier. So if you pick an energy functional described this way, where we have parameterized the wave function, then upon a suitable choice of a wave function, if you minimize this energy functional with respect to the parameters theta, then the energy that you obtain is an upper bound to the true ground state energy. So this is really the Rayleigh-Ritz variational principle that I'm stating, and which we have shown in this drawing. And this is what the VQE algorithm relies upon, except that the energy functional is evaluated on a quantum device, because we have reasons to believe that when this is appropriately evaluated on a quantum computer, then that would be hopefully much more efficient than on a classical device. The parameter update is done on a classical computer. So in this sense, VQE is a near-term or NISQ era algorithm, which is a hybrid of quantum and classical steps in this sense. So if you're interested in this topic, then you could go through some of our papers and preprints on this algorithm, which I've given here as QR codes. And I'll now move to the Harrow-Hasidim-Lloyd, or the HHL algorithm, the fault-tolerant error algorithm that we work on. Really what it does is to solve for a system of linear equations. So if A is an n by n matrix which is known, B is an n by 1 vector that is known, then you want to find X by evaluating A inverse B. And this is really what the HHL algorithm does, but this is of course a quantum algorithm as opposed to, say, for example, conjugate gradient or other such classical approaches that you're accustomed to. And if you recall the drawing that we saw in the first slide, a hard problem becoming simpler. In this case, you have an exponential speed up in the sense that the problem becomes exponentially simpler, so to speak, quote unquote, in system size upon using the HHL algorithm. And what we often extract is a feature of X, which could be an overlap or an expectation value or a transition matrix element. Again, these are terms that you would have come across in your quantum mechanics courses, and quantum computing heavily relies upon linear algebra and quantum mechanics. So what we did in this work, whose QR code is available here and which got published recently, a few months back in Physical Review Research, is to find the connection between the HHL algorithm and quantum many-body theory. And we also introduced what's called the Adapt HHL Lite suite of variants of the HHL algorithm for different quantum computing eras. So although HHL itself is a far-term or fault-tolerant era algorithm, we did introduce different variants for NISQ, for late NISQ, for early fault-tolerant, and then the fault-tolerant era itself. So lastly, I'll talk a bit on the quantum annular eigensolver, or the QAE algorithm, and our work can be found here. Basically, our goal was the physics goal was to find the fine structure splitting of highly charged ions, but using the QAE framework. And QAE relies upon starting with the familiar energy functional. And here all we do is take psi and express it in terms of linear combination of n particle basis functions, what's known as CI. And then we have to encode it because the quantum annular hardware is not universal like the gate-based hardware, but is more suited to solve optimization problems. And the functional that it can handle is of a very specific nature, often called the QUBO form, which we have showed here. So we pick the physics problem, we encode it to the QUBO form, and then we solve for these small QIs, basically. So we carry out several quantum anneals for a given lambda. I'll not get into what a sub-QUBO means here, but the idea is to then obtain the set QI, back convert and calculate the energy, and upon repeating it a few times, what I've just called a repeat, you'll be able to get your energies this way. And because fine structure splitting, as you may again recall from quantum mechanics or your atomic physics courses, involves the energy difference between two levels, we do it 2 times and take the difference between the two energies. And the remarkable part about this work was the kind of accuracy that we would achieve, which you often do not expect from gate-based quantum computers, of 99% for the systems that we chose. And the qubits we employed are 190, once again, very different in flavor from what you're accustomed to from gate-based hardware, where we often work with single-digit or double-digit number of qubits. And yeah, we have just compared it with some benchmark results here. So hopefully with this very, very brief overview, I've given some flavor of the sort of work we do in quantum algorithms at our center. So I'll just quickly show a slide on our research collaborations. Professor Das, of course, spoke about this, so I'll just leave it here. And Professor Das also mentioned that we have a lot of publications in leading journals. So it's basically the same thing here. So thank you for your attention, and I'll request Dr. Shivdas to give the last talk for the session, after which we can take questions from the students if there are any. Okay, Shivdas, we are not able to hear you. You're not on mute, but somehow we are not able to hear you. Okay. So I'm not able to hear Shivdas. Is someone else able to hear him? No, probably not.
No, we can't hear him.
Okay.
One possibility is that he can do what I did. He can, email you his slides.
Okay.
And you can sort of project them, and he can speak, I guess. Oh, we can't even hear him. Oh, okay. If you can't hear him, then this, yeah.
Yeah.
Then there could be an internet problem, I guess.
Is he muted, or he has some problems with internet? Or?
Oh, he's not muted. Perhaps there is some setting that he needs to change in order to be audible.
Mm-hmm.
But I'm guessing he's working on it as we talk.
Maybe one can call him and find out.
Yeah, sure. I'll just call him and find out.
Hello, am I audible now?
Yeah. Yes.
Okay, maybe it was my Bluetooth headphone that was the problem.
Okay.
So I'll directly use the microphone of my laptop then. Am I audible clearly now?
Yes.
Okay. So Prasanna, am I a co-host already? Then I'll share my screen.
Yes, you're a co-host already. Yes.
Okay. Let me share my screen.
Yeah, we can see your screen.
Okay, is it moving?
I'm sorry?
Can you see my the screens were moving, right?
Oh, yes. They are.
Okay, I'll do one thing. I'll not turn on my video if that's fine. Let me just check if it is fine with the video. Am I visible?
Yeah.
Okay. All right. So, good afternoon, everyone. So I am Dr. Shivdas Roy. I'm an assistant professor of quantum engineering at CQuERE. So I would like to call my group, of course, I'm a theorist, and so my group is a theory group, but it's more from the computer science perspective. So this is just background about me. Like, I'll just skip this slide maybe because others didn't talk about it. So the group members in my group are like Sanchita, Anant, Aster, Anumita. So Anumita will be starting her PhD. Like, she's already doing her coursework. She'll start her PhD research under me soon. Aster is an external student who's doing PhD, who's doing BSMS at ISER Tirupati, and the thesis is being done under me. Sanchita and Anant are interns, and earlier we had another intern who was Sushti Patil. So she already has completed her internship under me. So these are the current collaborations. I've just listed the external collaboration. And of course, we have also internal collaborators, like I work closely with Dr. Prasanna and Professor Mukherjee as well. So these are various collaborations that are external at the moment. So I've not gone into the technical details much, but I've just listed the various topics that I work on and what are we actually trying to do there instead of going into the technical details much. So the first topic is quantum algorithms, where the primary goal is to explore the limits of quantum computers. So currently, the understanding, as Prasanna already mentioned in his presentation, is that quantum computers are known to solve certain problems efficiently that are otherwise intractable for classical computers. So we still don't know how far is the power of quantum computers really. So we still don't know. Okay, this is the limit up to which quantum computers can solve efficiently, and beyond that, it's not possible. So it is important that we identify that limit, because unless we know the limit of quantum computers, its true potential will not be unleashed. More importantly, we cannot be truly prepared for the threat that quantum computers pose to the security of information processing and communication encryption. So unless we are sure that, okay, this is up to where quantum computers can be effective, we won't be prepared. We will not be able to combat the threat that quantum computers can pose to the communication security and also, security of various information processing systems. So to this end, we strive to design efficient quantum algorithms for increasingly computationally harder problems. So for example, we are tackling problems like traveling salesman problem. We are looking at problems like, certain hard problems such as quantum state distinguishability and other such problems. So the work under this category, it involves mainly designing novel fault-tolerant quantum algorithms. As already Prasanna mentioned, fault-tolerant are the far-term quantum algorithms that quantum hardware for which we are actually designing the algorithms. So it involves designing novel fault-tolerant quantum algorithms and also analyzing their errors and quantum computational complexity. So that is very important, because unless you're coming up with an algorithm which gives you computational advantage, there's no point of coming up with a quantum algorithm which otherwise could have been done on a classical computer with similar complexity. Besides, we also perform proof of principle demonstrations of our algorithms by running them on current NISQ hardware. So NISQ stands for Noisy Intermediate Scale Quantum Hardware, as you already know. Upon doing certain appropriate customizations to them, to the algorithms to suit the NISQ devices. So this is a broad overview of the work that we do on quantum algorithms from the computer science perspective. Of course, since this involves a lot of other analysis, and having to run on hardware, it's not like something which is something standalone and different from, let's say, what Prasanna and others do. But the analysis from my perspective is more from the computer science perspective. Next, quantum machine learning, not that we are doing a lot under this, but the primary goal here is to devise what I would like to call self-aware quantum machine learning models. Currently, machine learning models, whether classical or quantum, they are really hard to interpret as to how they work the way they do. Even their inventors, they cannot precisely predict the behavior of machine learning models on unseen data. So no matter how well trained, a machine learning model can still go wrong on an unseen test data, even if the chance is less than, say, 0.1% or 0.01%. But there are applications where even the slightest of error by a given machine learning model may not be acceptable. For example, a self-driving car can still kill a person, or a face recognition system can still let someone unauthorized to access classified information or enter restricted buildings. So to this end, we are striving to develop a quantum-inspired machine learning model. So the machine learning model could well be a quantum model, or it could be a quantum-inspired classical model. So we are looking at developing such a model that exploits principles of quantum mechanics to be able to detect beforehand by itself if it can go wrong on an unseen test data, in which case it can stop itself from making the error and instead take an alternative course of action as pre-programmed by us. So that is the objective of this work under this category. So of course, this is still something we are developing, and if this is successful, then we can actually look at expanding that work to different contexts, like to different kinds of machine learning models in the quantum domain. The next topic is quantum information. So we are also looking at problems in quantum computation that are not just limited to quantum computation, they are more general problems in quantum information processing, such as quantum state tomography. So quantum state tomography is actually the task of estimating a given arbitrary quantum state. And it usually requires multiple copies of the state because of quantum no cloning theorem and the fact that a measurement collapses the quantum state to a classical state. So this is a huge bottleneck in many quantum information protocols, including in quantum computation. So there are many applications or even quantum algorithms that you run on quantum computers where the rest of the algorithm is very fast, very, giving computational advantage. But then at the last stage or whenever you actually have to infer the state or you try to estimate the state, that computational advantage is lost. So this huge bottleneck is something which we should actually address, and that's what we have been trying to do in one of our works. So to this end, we have designed a novel quantum state tomography protocol that requires only a single copy of the quantum state of interest without knowing anything about the evolution dynamics of the state or without destroying the original state with measurements, so that the given state can be reused for any further quantum processing unscathed. So what we have done is we have actually used a single copy of the state to be able to estimate it, and that too we need not know anything about the evolution dynamics, such as the Hamiltonian that would have evolved the state to the desired state. You know, we don't know anything about the evolution dynamics of the state, and neither do we perform any measurement directly on the original state, so that the original state remains unscathed. That is, it is not disturbed, or it can be further reused for any other quantum processing. So a major implication of this work is that our algorithm can break the quantum key distribution protocols as long as it is enough to reconstruct the quantum state, the arbitrary quantum state of interest, only approximately. So one limitation, or one, I wouldn't say limit, but it's it's something that like almost all quantum algorithms do, is that they use a polynomially and not exponentially small precision. So in this case also, if it is enough to reconstruct the original quantum state to only a polynomially and not exponentially small precision, then it is likely that our algorithm can break quantum key distribution protocols. But of course, in most cases, it is important that you have an exponentially small precision to be able to break something like quantum key distribution. So finally, this topic is an interesting new avenue, I would say. Well, not very new, but still it's fairly new compared to other areas in quantum information science. That is to use noise as a feature rather than a bug. So the primary goal here is to explore the possibility of exploiting noise rather than avoiding it to improve and/or assist in quantum computation and/or quantum information processing. So as you know, currently the biggest problem with quantum computers is noise. It is increasingly becoming impractical to be able to scale up quantum computers because noise cannot be fundamentally reduced beyond a point through engineering advances only. So unless we look for ways to use noise to our advantage rather than avoid it, the second quantum revolution, at least as I see it, is bound to end in what is called a quantum winter. So to this end, we would explore. We would explore how current noisy intermediate scale quantum hardware, NISQ hardware, can be used judicially in a clever manner to do as good as, or even possibly better than, what is known to be possible on future fault-tolerant quantum computers. So why do I even saying this? Because the motivation for such a possibility comes from some of the existing literature, including a previous paper of mine suggesting that it is at least theoretically possible to do various quantum tasks better with noise than without noise in some situations. So, of course, you can look at some of the references that with the titles like noise assisted, let's say quantum certain algorithm and all. So you'll see that there is some literature already existing where people talk about using noise rather than avoiding it to be able to do at least as good as what you can do without noise. And in fact, theoretically, it has been demonstrated in various papers, including mine, that it might be possible to do better with noise than it is possible without noise. So maybe we can do certain things on NISQ hardware itself, which otherwise would not even be possible on the future fault-tolerant hardware. So to this end, we are actually thinking of coming up with some clever way of exploiting the noise in a positive manner rather than avoiding it, so that it's possible to do tasks which are otherwise out of reach for current hardware or even for future hardware, if at all it's possible to scale up quantum computers to that extent. All right, so that's all from my end. If you need more information, you can go to my personal website, which I've listed here. You can write to me at my official email ID or my Gmail ID. You can find my publications on Google Scholar here. And of course, my profile you can see on CQuERE website as well. So yeah, that's all from my end. Thank you.
Thank you so much, Shivdas. And I think with that, all of the faculty members from CQuERE have presented their works. So if I'll just check if there are any questions on the YouTube chat. It looks like there are no questions on the YouTube chat. Okay. Yeah, I think I'll then request Professor Das to conclude in that case. And I'll just add
Okay.
note that if anyone has any questions, they can always write to us at any point. Who are students watch this at a much later time. Yeah.
Okay, so thank you very much. I think so. We've covered all the presentations now, and thank you, Prasanna, for moderating. I would now like to invite questions from the students who are attending, and you can make comments or ask questions. Okay, I mean, if there are no questions, please feel free to write to us. You can email any one of us whose work you found interesting, or you can write to me if you want to know about our center, about our overall activities. So we will be advertising for PhD students fairly soon, and you're most welcome to apply for it. So I think that's all. I can see Sobhik.
Yes, sir.
Do you have any questions, any comments, Sobhik? I mean,
No, currently no, because I'm already working with Pankaj, sir.
oh, no, I know, but okay, all right, fine.
Yeah, I just wanted to know when will be the advertisement out for the PhD.
Yeah, that I think Professor Deb might know. We'll have to talk to Anubrata Chakravarti, who's the ACSIR coordinator.
Okay.
Yeah, maybe you should talk to him. And if he doesn't know, he can talk to people at ACSR and find out for you.
Okay, surely.
Yeah. See, as I told you, I mean, it doesn't matter if you've not taken any national entrance tests. You know, we will give our own entrance test.
Yeah.
So that should not prevent you from applying for a PhD.
Okay.
Any other question? Okay, in that case, let me thank all of you once again, and we will continue to reach out to the students, to the potential students, and I don't know. I mean, if time permits, we can also invite some students to visit us at our center. It should not be difficult to invite local students from Kolkata. Yeah, outside of Kolkata may not be so simple, but so let's think about that. Let's think about different ways of reaching out to students and letting them know about our work. Okay, then. So thank you very much, and so that finally brings us to the end of this meeting.
Okay, thank you very much.
Thank you.